Thanks for that wonderful introduction, Frank. Okay, as Frank said, I'm with NOAA at the Atmospheric Turbulence and Diffusion Division. It's a lab that is involved in a number of things. It's involved in climate observing systems, boundary layer physics, some air quality modeling, and also some air chemistry measurements. I thought I'd put this up here before. I think in my career, I think at one time or another, someone thought I did this. So when you start in the upper left-hand panel, what society thinks I do, what I think I do, what my grandmother thinks I do, what my friends think I do, what I actually do, and what people I meet think I do. My son gave me that, and I thought it was quite appropriate, so I thought I had to put that up there. And this is how it started. I was a graduate student at here, and the department was moving from main campus to North Campus, and my job, summer job, was to put up this tower. That was the beginning of my interest in instrumentation. So that was my summer job, and then along with Bill Kuhn and a couple of other faculty, about a year later, they got a grant to measure and teach things about solar energy. So my job was to instrument this and bring the data in. And so I got interested in solar radiation, thus my thesis topic ended up on understanding the diffuse radiation component. So that's how I got started in instrumentation.
Where is that?
That is actually, that table's still on the top of this, on this building over there. So there's still remnants of Bruce Baker floating around here still, after 20 or 30 years. So today's talk really is all about the importance of in situ observations. How do you use them? How do you validate? How do you incorporate those into models and understand it? What research goes into it? And also from a climate perspective. So how do these in situ observations really intertwine with other methodologies for measuring parameters or modeling the atmosphere? So we're going to start with climate observations. And the first thing we're going to talk about is the U.S. Climate Reference Network. It's a NOAA network. There's 114 stations in the U.S. And it's really designed to answer the question, how is the national temperature precipitation changing with the highest confidence possible? And the unique thing, one of the few unique things about this is that the measurements are triple configuration. So there's 3 independent measurements of temperature, there's 3 independent measurements of precipitation, and we have ancillary measurements. We measure solar radiation, we measure skin temperature, and we also measure wind speed. And the thought is that we would like to have this in the ground for 50 years and have them in pristine areas so urbanization doesn't affect them. So actually when we sited these stations, one of the things we really strive to do is to make sure that we put them in places where we wouldn't have to worry about that. This is sort of a history of the climate observing system in the U.S. It started with diaries and logs. Actually, Ben Franklin and Thomas Jefferson kept them. Actually, some of their diaries and logs are archived at the National Climatic Data Center. The U.S. Army forts, actually, they measure temperature on a daily basis, and there's a data set for that. So we go up and we finally get, to the Cooperative Observing Program. That's the one that's been used in the past to look at climate change. It really wasn't meant for that purpose. It was really meant to monitor the weather, the max min temperature, things of that nature. But it was really the only network that was available for looking at climate change. So there's about 13,000 of those. And so out of that, one developed the U.S. Historical Climatology Network, and that was a subset of about 1,100 stations out of the 10 or 12,000 other stations. And those were picked because of their period of record, no station moves, very few changes in instrumentation. So you had some concept of being able to get at the climate signal where you wouldn't introduce these discontinuities. There's been attempts at modernizing the co-op. They haven't been successful. And then in about 1999-2000, we started to develop the US CRN program. It became fully funded by NOAA in 2000-2001. And we were able to hold this whole system out right around 2008. There has been an attempt to look at the regional climate signal, developing a regional climate reference network. Unfortunately, that's been zeroed out of the budget, and I don't think that's going to fly. But we hope to keep the USCRN going for a long period of time, and hopefully it's been over a decade, so we've been fairly fortunate and lucky to maintain that funding to eke out the climate signal. It's really the only long-term network in the United States that's designed for that. And it's actually been beneficial to the Weather Service too for short-term forecasting. So like I said, there's the 114 stations. And this is the sort of the layout for one. This is a wooden fence around the rain gauge. It's really meant to stop the wind flow so you have an opportunity to be able to measure solid precipitation. We'll see some things later, examples of that, where without this type of fence around it, and if you don't stop it, you create a boundary layer on that gauge so the lighter the snow particles, they advect away from the gauge and just never measure them. You can't see the third one, but there's 3 aspirated shields with temperature sensors in them. There's an anemometer here. That anemometer was put there for a purpose. We thought we'd eventually, with this system, if we designed it properly, that we'd actually be able to get at the water budget and evapotranspiration terms. And one of the things you need for that is going to be a wind speed at the temperature measurement height, and that's one of the reasons it's there. This little thing here measures solar radiation, and then you can't see it, but right at the end there is an instrument that measures land surface, skin temperature of the surface, and we're going to talk about that a little bit later in terms of how that's been used to validate satellite land surface temperature measurements. We have added soil moisture, soil temperature to each of the stations. So one of the, I think, gaps in understanding convective initiation, climate change, drought is the fact that it's really been a paucity of soil moisture measurements. So we now have soil moisture measurements at about 108 sites. There's just some places you can't physically put them. So that's sort of new. So we're hoping to see that that science move forward with those. We're also embarking in Alaska. That has its own challenges, obviously. You know, it's quite a remote places. You got to fly in by helicopter. Some places, sometimes you have to camp. Obviously, power is a big deal. So, in this situation, there's very few, if any, that are AC power. Mostly, it's solar panels and fuel cell technology that we're using for power management. This is what can happen. This is in Barrow, Alaska. Actually, a polar bear did attack our temperature measurement systems. And we did get it fixed, but you know, these are some of the hazards, some of the difficulties you find in remote places like that. This just to give you some idea where some of these are located and trying to maintain the you know, siting at pristine areas. This is Barrow in Alaska. To contrast that, we actually have one in Death Valley also. This is in Redding, California, and this one's in the south in McClellanville in South Carolina. So. And we also don't ever pick private property. It's all public property because we do know if it's on private property and ownership changes, you know, that owner may not want that site there. So we've been fairly fortunate over the decade. I think we've had to move 1 or 2 stations out of 100 so far, and it usually had to do with development. Some of the records we've seen 126 degrees for an air temperature in Death Valley. Lowest temperature we've seen is -56 in Barrow. We've seen ground surface temperature actually higher than 160. There's been a couple in Texas that they had a pretty extreme drought in 2010, 2011, and we saw 175 degrees for a surface temperature there. Just no water there at all in the ground. And the lowest ground surface temperature, again, at Barrow, Alaska, of -60. So that's pretty remarkable to see these types of numbers in the atmosphere. The other thing we contribute to now that we got the soil moisture sensors in the ground is the National Integrated Drought Information System. We contribute to the drought monitor, and actually Obama's climate plan includes developing a strategy for an integrated soil moisture network, and the Climate Reference Network is actually going to be part of that plan along with a number of other networks, but we're also trying to couple in the models that are used to monitor drought and also passive sensing. Just to give you an idea, here's just, so we don't have a long data set, we can't talk about trends, but we can talk about changes. So this is June, July, and August. So 2011 examples have changed from 2010 to 2011. But you can note that this is overall depth. So the depths are from 5 centimeters to 100 centimeters, and we just sort of average those together. So when you start seeing values of 0.1, that's an extremely dry situation. So certainly that's evident in the west and the southwest. Around 0.3 it would be considered saturation. So you can see in the northeast and the Ohio Valley that they're about on par or good. But certainly it's quite evident that here in the west and southwest, they're certainly in an extreme drought situation. This is the regional climate network. It was designed to be similar to the climate reference network, so the same instrumentation is used, the same data logger, the same QA/QC, and the same transmission methodology, so that it gave us an opportunity, if indeed this got off the ground, we would have a regional climate reference network that was standardized back to our national reference network. So unfortunately, funding stopped in 2013, so I don't know if this is going to fly or what might happen to it. There's 71 stations in that network in the west, and there's 13 in Alabama, and it's just going to be interesting to see if we can somehow resurrect that or if it falls by the wayside. Once again, once you start getting into a regional network, you start running into issues of, since it's more dense, is trying to find those pristine areas or try to keep them pristine. Just some other examples. Now we're going to switch a little bit and talk about evaluation and validation using our skin temperature measurement from the climate reference network, and how well can we actually use those to validate satellite measurements or for land surface temperature, and also the model component. So we did a study. We started with a site that was in Crossville, Tennessee, and we actually had satellite data from Aqua and Terrace. We actually had an airborne flight, and that actually was looking at the variability within the satellite pixel itself. So that gives us some idea of what the integrated value would be compared to what the satellite was seeing. We also then compared this sensor, this airborne sensor, its integrated value, to how well or how representative that 1 point value from the CRN site would validate with that. So we started with a grand scheme, trying to cover lakes, desert, grassland, forest. I think we did a pretty good job in an agricultural region. We did a pretty good job with a heterogeneous region and a forested site, but funding ran out. But we did, I think, get some interesting results of the possibility or the capability of using these in situ measurements to validate the satellite measurements. To recap, what we're doing here is we got satellite, aircraft, and in situ measurements, and we want to see if we can, how well they validate, how well they compare, and can the CR network, which is just that point measurement, really be something we could use to validate with, because typically satellites have used the 2 meter temperatures because that's all they had. And we certainly know that the differential between the surface and the 2 meters can be substantial, especially in the transition period in the morning. Uh-oh.
Unless you pulled out the dongle for that.
No?
Instead of the drought.
No, the whole thing came up though.
You used the button. I have the chair.
All right, let's try this. Oh, that's going backwards. So this was the objective, to look at land cover over lake, grassland. We were successful on a couple of land surface land covers, but not all of them. So this is Crossville, Tennessee, and superimposed on that in that shaded area is the MODIS pixel. That's the integrated value for the satellite itself. And let's see if this works. Yeah, okay. So the tower is the black line. The purple is the aircraft. Those are the observations with the aircraft. And also the blue line is the aircraft. It's 2 days in there, or 2 passes. And then the red dots are actually the satellite measurements. What we've noticed with the satellite measurements, that at the peaks, which is going to be sort of in the noon, or at least it's well mixed at that point, we see fairly good agreement with the satellite land surface temperature. But what we find when we get to minimas, typically that's going to be in the morning, or it's a transition period, so that surface layer from surface to 2 meters is not well mixed, and it seems to be a little cooler than it should be during those periods of time. Another example, in this case, this was in November, so we know that it's fairly homogeneous. There's not a lot of plant life going on, and we saw quite a good agreement between the aircraft and the tower within a degree. This is an example of the data points. These points represent the land surface temperature measured from the aircraft. This is the pixel, and this is the CRN tower down here. You do note right here we had an anomalous that's water right there, and you can see that we had much cooler temperatures when you look at aircraft minus tower. That's just pointing those features out. I'm going to skip that one. This part here. So in this data set, if we look at the satellite and tower, how well do they agree on these particular days? We had to pick clear sky days. It works the best in terms of looking at how they compare. But you can see some differences up to 3 or 4 degrees difference between the tower and LST, or land surface measured by the satellite. And this is over the whole observing period where we had data. And you can see again, what we see is that in these minima, that the satellites are sort of not as estimating as well as with the tower and aircraft, but certainly on the maxima they are. And I think this is just due to the transition periods, but just not well mixed in the area that the satellite's trying to measure the land surface temperatures. This is sort of overall where we got a lot of MODIS data for all clear days for about 6 months. And we see that we have about a 2-degree bias between ground-based LST with our CRN measurement as compared to MODIS. And this is sort of the histogram or distribution. And it shows that, and the median is probably within a half a degree, but with a variation of about 2.7 degrees. So really that's not too bad. It does say that for that particular location, there's an opportunity perhaps with the CRN to actually use that for validation for satellite land surface temperatures. These are some other areas. This happens to be in Bonneville. This is where I was telling you that it's very heterogeneous. There's a cornfield, there's a field, and the CRN is sitting in a grass field. And so the CRN's down here. So really the thing to look at here is how well is the aircraft data and the satellite matching up. And in this case, we didn't have the aircraft data here, but you can see it's significant difference just in the surface temperature. So we know that it's heterogeneous. So we do know in a situation like this that it's really not going to be something where we can get a reasonable validation. So here's 18, 3 degrees difference there, and a degree or so there. And that's on October. That's the best you're going to get. During the growing season, when you start in May, you're really suppressed. You start seeing 3 and 4 degree differences between satellite and the CRN data. Same thing on that day. We're still in May. Now the other aspect of this is a land surfing model. It's just a one-dimensional model, but the way that it's calibrated is we take information from the Climate Reference Network, which is incoming, outgoing solar radiation, latent heat of evaporation, and also the land surface temperature. That's put into the model, and then a Monte Carlo technique is used. This is used to calibrate the model, then a Monte Carlo technique is used to converge so the differences between the model and the measurements are minimized. From there, it's upscaled, and from there, then you try to compare it to what the satellite's doing. Okay. So Crossville, we see that the model's doing a pretty good job. Here's the point measurement, and then here's how the model did with both satellite and the model itself, and fairly good agreement. So we're pretty pleased with that, but that's the easy case. Chestnut Ridge is a little different. That's near our place in Oak Ridge, but it's a forested area. So as far as land surface cover, it looks fairly uniform because it's mostly green. And we find very good agreement between the model and the tower. We didn't have aircraft data here. But again, you'll note at these minima, I still think that's the transition period where things are just not well mixed, and what the satellite sees and what is happening is slightly off, slightly cooler. Now we're going to switch one more time. This time we're talking about flux measurements. And this is a study that was being conducted to look at fluxes of CO2 and methane in the permafrost regions of Alaska. National Science Foundation funded it. Harvard's involved. It's actually Jim Anderson's group that's involved with that. He's developed the chemical or the laser systems to measure methane and CO2 with a fast response. And our lab, oh, it did work. And our lab has developed the instrument that goes on the nose of the plane. It's got pressure ports on it, and you look at the differential pressures, and from that you can get the UVW fluxes of the wind. So if you couple these UVW fluxes of the wind with these chemistry measurements on the backside, you can actually start looking at sources and sinks for methane and CO2 in the permafrost regions. And the whole concept here is what's the magnitude of the melting permafrost, what's it contributing to greenhouse gases? What are the science questions? I'm going to run through these pretty fast. What is the flux of methane evolved from the thermokarst lakes? What's the variability among lakes? What's the contribution from the soils? And it's really sort of tricky. We'll get to that point. So this is the beginning of the program. We actually took our probe, went to the MIT wind tunnel to calibrate it. And this is the team that put it together. This is the plane. There's the probe at the end that's measuring the fluxes. And these are the different laser systems. You've got a methane and a carbon dioxide axis. You've also got a methane isotope axis. And this illustrates what we're doing with the BAT probe. The methane isotopes, hopefully, now these are data that you're going to see literally came out this week, so we're still in the preliminary stages. But if we can get at the isotopes of both methane and CO2, there is an opportunity to try to understand what's going on, whether it's biogenic or thermogenic, that's producing these extra pulses of methane and CO2. This is our flux tower. It's measuring water vapor, CO2, and this instrument here is an open path methane sensor. So the pilot was pretty brave, flying quite low, as you can see. And really the point of this is you can see some water here, but you also see a patch of land. We know what the footprint is for this station with respect to its surroundings. And to get the flux, we want to get this plane to calibrate against this in situ tower. And then we want to be able to understand what size flux print that is, so when the plane starts flying different transects, then we can say something about what those fluxes are over a larger piece of land. There's the flying again. And so these are the concentrations in ppm. Typically, most of the time, it's a short duration, it's only August, but typically you see about 2 ppm, but we certainly saw some peaks up to 4 ppm, which is almost twice of what the background typically is. We are going to go out, this year we're going to go out, we only did the month of August this last year. This year we're going to go out before the permafrost melts, probably in May, and keep it there until it actually refreezes back in probably September to see the onset and cessation of this production, to see if we can make some better sense of what we're finding just in that short month. These are the CO2 fluxes. The thing to note about that is the large excursions in terms of the magnitude. That's a pretty big deal. And this is hot off the press. These are the fluxes of methane from the plane. There's certainly some hot spots, the red. So we fly these transects. Here's our tower. We fly out of the Dead Horse Airport. And then we do these transects. We do our calibrations, and then we start looking at fluxes. These fluxes are calculated by looking at the surrounding land. So if you're trying to eke out the land signal and it's going over water, you subtract that out of that piece, so that when you look at this integrated value across that path, then you have a better idea of how to calculate a loading of the atmosphere, because it's going to be different between water and land. So that's the concept. But we do see some hot spots. Typically 1.5 or 2 micrograms per meter second is about right. But when you get into greater than 3 micrograms, that's truly a hot spot. And it's certainly probably due to the permafrost melting. This is just, doesn't look like much, but actually it's a calibration run. And where we have, this is the time series from the tower, and this is the points that we're able to eke out of the aircraft. And we think that they're doing a pretty good job of comparing. So finally, we're going to talk about a solid precipitation intercomparison. This is where we're taking different instruments that measure the same thing and try to understand how well they're doing. Because we do know, in most cases, in most countries, we're not doing a very good job of measuring solid precipitation. So we're trying to improve the understanding of the performance of different solid precipitation gauges, try to develop transfer functions between different systems. Some have shields, some don't have shields, some gauges are shaped differently than others. And also try to define a field standard for solid precipitation measurements. So we're trying to bridge the gap between the previous WMO study, which was done back in the 1990s. And of course, all those were manual measurements. There weren't a lot of automatic gauges. So the key here is to try to look at what now the technology's designed with the automated gauges. And also what's happened, of course, through that time as there's been new shield and gauge technologies. So, and again, let's try to provide some standardization for solid precipitation measurements. So there was a survey done by the WMO, and of those countries that are involved with the WMO, 51 member countries responded, and 45 actually provided detailed information on their precipitation measurements. So remarkably, only snow water equivalent is the melted snow. That's typically the type of measurement you want. Only 17 of the 45 countries actually make that type of measurement. And how well they do that, we don't know. And other respondents measured at least one parameter, but that could have been snow on the ground or snowfall amount. But the snow water equivalent is the one that we're really interested in, because that's going to give us a better idea of what the water budget is just due to solid precipitation. So this is why we're doing it. That's our gauge in Barrow, and this is the one. These are taken at Marshall, which is our test facility. As you can see, obviously, it's when they're not heated, it's very difficult to get an accurate value for solid precipitation. What's the problem? It's really the flow regime. You've got this object. It's a cylinder, but this is its shape, and as the wind speed increases, it's going to create a boundary layer. And depending on the type of the snow, and the finer the crystal, the drier it is, the more it's going to be advected away from that orifice, and therefore we won't measure it. And here's a good example. These are actually measured values. This is a collection efficiency with a gauge with a single altar around it. And then we used a flow simulation model, and we did different types of snow crystals. In this case, this solid purple line is dry snow, and this dashed purple line is wet snow. And they sort of fall in between what we found. The key here, the thing to take away from this, is when you get into the 4 to 6 meter per second, you've got anywhere between 80% to 100% reduction in being able to actually in collection efficiency, which you're basically not measuring at that point. And to consider that solid precipitation probably contributes to about 30% of the global precipitation, and we're underestimating by 80 to 100%. That's a significant thing in terms of looking at water hydrology and water runoff and water for people. So here's some of the problems you encounter. This is a single altar. You can see a significant drop off when you get into the 4 meter per second range. These shields are two shields. It's called a double altar. There's an inner shield and an outer shield around the gauge. Again, you see these drop-offs. But when you compare the standard, which is the big wooden fence, to the type of fence we have around our CRN site, you can see as a function of wind speed that actually it is fairly good. It's not dropping off. Fundamentally, the reason for that is that it's a type of fence that is significantly reducing the speed prior to getting to the gauge. So if you're significantly reducing that speed prior to getting to the gauge, then you're going to be able to increase your collection efficiency. This is hot off the press. Most countries have no shields around their gauges at all. In fact, the U.S., Canada, Japan, and China, I think maybe the Russians do too. But so if you have a gauge with no shield around it, and this is what this is showing. This is a gauge with no shield versus our reference, and you can certainly see that you're in the 5 to 6 meter per second range. You're really going to be about a 50% reduction in being able to measure solid precipitation. This air thing's working pretty well. I haven't attempted that one yet. So, where are these sites located for this WMO study? We've got different countries involved. It's good that we do. That way, we've got different climate regimes. But it is a challenge in organizing data and getting everybody to bring data in and standardize the data and try to get it into one place so we can do analysis. That's a real challenge in this case. This is in Australia. I'm just going to show you some pictures. This is in Brotts Lake, which is in Saskatchewan. It's on the plains, western side of Canada. This is Brotts Lake. This is actually trying to emulate Tretkioff shield in a bush gauge. The bush gauge was the original standard. that the Russians developed. So obviously you're blocking the wind there, so you're hoping that you get high efficiency catch under those circumstances. This is Canada. Canada's the one leading the effort for this effort. The U.S. is second in command there, I guess. That's our group. This is Finland. We chose this for a particular reason. It's surrounded by trees. So by putting in different rain gauges or snow depth measurements, just to see how well they compare in the field, but yet not have to be worried about wind. What's that going to look like? So it's sort of our zero order site to see what happens without any winds at all. This is Norway. They get extremely high winds. This is Switzerland, just outside Davos. This is New Zealand. They actually had, where this is located, they actually had to helicopter everything in. This is Chile. And this is the site in Boulder. We started out, this is our Climate Reference Network test bed, and we've expanded that for this experiment. We probably have about 150 different types of instruments that measure precipitation: optical, acoustic, GPS, and almost every type of weighing rain gauge that's made. So this has been going on. This will be the second year. And it's probably got another 2 years of collecting data before we'll try to standardize stuff. But we already have data analysis team trying to come up with techniques to look and see how we're going to develop transfer functions and see how we're going to be able to adjust values from other gauges that have different configurations. And that's Poland. Poland's involved mostly with snow depth measurements. This is Japan. They have 2 sites. And this one is important. Valdai was where the original experiment was conducted for looking at reduction in collection efficiency. So we really wanted to keep them participating because that's sort of our anchor point to go back to see how well, see how what they're doing and what we come up with the automated gauges, and use this as the anchor point. And that's the end.